the integral test, and estimates of sums. Consider the following series. We have the summation from 1 to infinity of 1 over n squared. The first 5 terms of this series are given here. Does the series converge or diverge? Let's look at the function that corresponds with this series, the function y equals 1 over x squared, and you can see the graph of that function here. If I go to x equals 1 and go up to the curve and draw a rectangle here, the area of this rectangle is 1 unit because the height is equal to 1. At x equals 2, the height of this rectangle is 1/4, and so the area is going to be 1/4. At x equals 3, the height is 1/9, and the area is also 1/9, etc. So I want you to notice that the areas that you see here are the terms of this series. So we want to know if these areas add up to be a finite number or not. Well, let's think about the area under the curve, 1 over x squared, from 1 to infinity. What if you were asked to find this area? Well, we know we can find this area by simply doing an improper integral. So the area under the curve here is the integral from 1 to infinity of the function 1 over x squared with respect to x. And this is the limit as t goes to infinity, integral from 1 to t. And 1 over x squared is the same as x to the negative 2. And now we'll go ahead and evaluate this integral. We end up getting x to the negative 1 divided by negative 1. And again, this is from 1 to t. Continuing, we have negative 1 over x evaluated from 1 to t. And then we will take the limit as t goes to infinity. And of course, this is the limit of negative 1 over t plus 1. And this is equal to 1. So we know the area under the curve from 1 to infinity is equal to 1. We also know that if we add up all of the rectangles starting here, the sum of the areas of all of these rectangles is less than the area under the curve. So what I'm saying is 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, etc., is definitely less than 1. And so if I add 1 to both sides, we have the sum n equals 1 to infinity of 1 over n squared is less than 2. Now, if you think about the partial sums of this series, every time you add another term of this series, you get a larger sum. So if we know that the infinite sum is less than 2, and if we know that the partial sums are increasing, then the partial sums here form a monotonic and bounded sequence. In other words, the partial sums are increasing, but they are always less than 2. And because of this, we know that the limit as n goes to infinity of the partial sums definitely exists and is equal to some number that we will call s, where s is the sum of the series. And we know that this sum is less than 2. So basically what we've proven here is that the series converges. So what I want you to understand from all of this is that there is a link between the sum of the series from 1 to infinity of 1 over n squared and the integral from 1 to infinity of 1 over x squared. And the relationship is both of these converge. Now, I want to be very careful here. They are not equal to the same value. So the sum of the series is not equal to the integral of the function, but they both converge. And we will find that they either both converge or they both diverge. Let's take a look at another example. Consider the sum of 1 over the square root of n. So it's a very similar type of series here. N equals 1 to infinity. You can see the first 5 terms of this sum are given here. And here is the function 1 divided by the square root of x. And if I go to x equals 1, I get the height of this rectangle here is 1. Therefore, the area is 1 times 1, which is 1. The height of the next rectangle is 1 over the square root of 2. Therefore, the area is 1 times 1 over the square root of 2, which is 1 over the square root of 2, etc. So what you should notice here is that the areas of these rectangles is equal to the sum of this series, right? In other words, each one of these terms here corresponds to the area of one of these rectangles. Now we can see clearly in this case that if I take the integral from 1 to infinity of the function 1 over the square root of x, that would be the area under the curve. And we can see very clearly that this area is definitely less than the sum n equals 1 to infinity of 1 over the square root of n. And you know this because you can see that the areas of all the rectangles is more because all the rectangles are above the curve. So let's go ahead and find the integral from 1 to infinity of 1 divided by the square root of x. So again, this integral here is going to be the limit as t goes to infinity, integral from 1 to t. 1 divided by the square root of x is the same as x to the negative 1/2. We'll go ahead and find the antiderivative, which is going to be x to the 1/2 divided by 1/2, which is the same as 2 times the square root of x from 1 to t. And so this is the limit as t goes to infinity of 2 times the square root of t minus 2. And this very clearly goes to infinity as t gets large here. So this integral is infinite. But we know the sum of the series is bigger than the value of this integral. So if the integral is infinite, the sum must be infinite as well. And so this series diverges. And so again, the value of the integral and the value of the sum are linked in terms of they either both converge or they both diverge. And this brings us to what is called the integral test. Suppose f is a continuous, positive, decreasing function on the interval from 1 to infinity, and let the term an be equal to f of n. The series summation of an is convergent if and only if the improper integral is convergent. In other words, if the integral is convergent, the series is convergent, and if the integral is divergent, then the series is divergent. Now, one thing you need to make sure of when you apply tests for convergence is you need to make sure that you are careful to check the hypotheses of that test. So the integral test can only be used on functions that are continuous, positive, and decreasing. So before you can use the integral test to draw a conclusion about convergence or divergence, you have to check that these three things are satisfied. So in our first example, we want to test whether the series summation 1 over n squared plus 1 is convergent or divergent. So let us first think about the function corresponding to this, which would be 1 over x squared plus 1. we need to check to make sure that this function is positive, continuous, and decreasing prior to using the test. Well, it most certainly is positive because when you plug in any value of x, this is always going to be a positive number here. It is also certainly continuous, for there are no values of x that will make the denominator equal to 0. And is it decreasing? Well, yes, and I would say that it is very obviously decreasing. If you plug in values of x that are greater than 1, the denominator of this fraction gets bigger, and therefore the whole thing gets smaller. Now, even though the fact that it is decreasing is obvious, we can still check to make sure by taking the derivative of the function. So to calculate this derivative, I'm going to view the function as x squared plus 1 to the negative 1. Therefore, the derivative would be negative 1 times x squared plus 1 to the negative 2, multiplied by the derivative of the inside, which is 2x. And this is equal to negative 2x divided by x squared plus 1 squared. And this is definitely negative for all positive values of x. And for a series, we only plug in positive values for x. So it is decreasing. So now that we know that those things are satisfied, we are just going to look at the value of the integral from 1 to infinity of the function 1 over x squared plus 1. So this is, by definition, the limit as t goes to infinity of the integral from 1 to t of 1 over x squared plus 1 dx. And this is the limit as t goes to infinity of the antiderivative of 1 over x squared plus 1, which is the inverse tangent of x from 1 to t. And we'll keep going here using the fundamental theorem of calculus. We get the inverse tangent of t minus the inverse tangent of 1. And as t goes to infinity, the inverse tangent of t goes to pi over 2 minus, and then the inverse tangent of 1 is pi over 4. And so the value of this integral is pi over 4, which means the integral converges. And now the integral test tells us if the integral converges, we know that the corresponding sum also converges. Now, just to be clear, the value of the sum is not equal to the value of the integral. But since the integral converges, we know the sum at least exists. For the next example, we ask the question, for what values of p is the series 1 over n to the p convergent? Just to be clear, this series has a name. It's called the p-series. And we've already discussed in the past that the integral from 1 to infinity of the function 1 over x to the p dx is equal to a converging integral if the value of p is greater than 1. Therefore, the sum n equals 1 to infinity of 1 over n to the p will also be convergent if p is greater than 1. Now, of course, we do have to mention that the function f of x equals 1 over x to the p is a positive function, it is a continuous function, and it is a decreasing function. And all of these things are true. Therefore, the integral test tells us that since the integral converges for values of p greater than 1, the series will also converge for values of p greater than 1. And as I mentioned, this series is called the p-series. And here we have the formal statement, the p-series, summation n equals 1 to infinity of 1 divided by n to the p is convergent if p is greater than 1, and it is divergent if p is less than or equal to 1. So for example, the series 1 over n cubed is convergent because p is equal to 3 and 3 is bigger than 1. And the series summation 1 over n to the 1/3 power, or 1 over the cube root of n, is divergent because here the value of p is 1/3 and 1/3 is less than 1. So the p series is a very easy test to apply. Next, we are asked to determine whether the series natural log of n over n converges or diverges. So again, let's first look at the function natural log of x divided by x. This is a positive function, yes. If you plug in any number greater than 1, natural log is always positive. And in fact, when you plug in 1, natural log is 0. So really this series could have started at 2, because when you plug in 1, you don't get anything. Is it a continuous function? Yes, it is continuous as long as we don't plug in x equals 0, which we are not. And is it decreasing? Well, for this, we need the derivative. The derivative of this function is the bottom function multiplied by the derivative of the top, minus the top function multiplied by the derivative of the bottom, divided by the bottom function squared, and this is equal to 1 minus the natural log of x divided by x squared, and this is less than 0 as long as x is bigger than or equal to the number 3. Okay, so in other words, the natural log of 3 is a number bigger than 1, and then when you subtract that from 1, you will get a negative number, and for any number beyond 3, natural log is also a number bigger than 1. So it doesn't have to be decreasing right away. It has to be decreasing eventually. So it is a decreasing function eventually. Therefore, it satisfies all the hypotheses of the integral test. So now we are just going to apply the integral test. Let's take the integral of the natural log of x divided by x. This is equal to the limit as t goes to infinity of the integral from 1 to t, natural log of x divided by x. Now, to evaluate the integral, we're going to use a u substitution. We'll let u equal the natural log of x. Du will be 1 over x times dx. And so this simply becomes the integral of u du, which is u squared divided by 2, which is the natural log of x quantity squared divided by 2. And so now that I have that antiderivative, I'll come back here and we'll plug that in. And now we'll plug in the upper limit of t minus the lower limit of 1. Natural log of 1, of course, is equal to 0. And so what is the limit as t goes to infinity of the natural log of t? Well, it is infinity. So this integral diverges, and therefore the sum also diverges according to the integral test. Next, we have what is called the remainder estimate for the integral test. Suppose that f of k is equal to ak, where f is a continuous positive decreasing function, and this is true for all x greater than or equal to n. And let's also suppose that the series summation of an is convergent. Now, if we define the remainder Rn to be S minus Sn, then we have that remainder is always a number in between these two integrals. Now, let's understand what the remainder actually is equal to. So S is the sum of the series, which is A1 plus A2 plus A3 plus A4 plus forever. Sn is the sum of the first n terms of the series. So the sum of the series goes up to the nth term, and then it continues on after the nth term, right? Again, it goes forever. So when we take S minus Sn, we are subtracting these terms from this sum. And so if we subtract those, all these terms here are going to cancel out. And what you're going to have left over is the rest of the terms starting with an plus 1. And we call this the remainder. So for example, if I look at R10, R10 is the sum of the series minus the sum of the first 10 terms. So that is going to be the sum of the 11th term, 12th term, 13th term, and so on forever. So it is what remains after we take away the first 10 terms. So this is why it is called the remainder. Now, when you're adding up a bunch of positive terms, the remainder is basically the error when you approximate the sum using the first n terms, right? So if you know that you have a converging sum and it converges to S, Sn is an approximation of that sum. Well, what is the error of that approximation? Well, the error is the remainder. So back up here now, we know that the remainder is a number in between these two integrals, and you can see that from these pictures here. So if the remainder is the sum of the n plus 1 term all the way out to infinity, we can see that that is less than the area under the curve from n to infinity. And that same sum, the remainder, is greater than, right? Because you can see that these rectangles are above the curve. It is greater than the area of the curve from n plus 1 to infinity. So that is where these come from. So if you calculate both of these integrals, you get an estimate of that error. So for example, approximate the sum of the series summation 1 over n cubed by using the sum of the first 10 terms, and then estimate the error involved in this approximation. So again, we know that the sum of the first 10 terms is the sum k equals 1 to 10 of 1 divided by k cubed. And this is going to be 1 plus 1 over 2 cubed plus 1 over 3 cubed plus 1 over 4 cubed, etc., right? All the way up to 1 over 10 cubed. And we'll go ahead and use a calculator to approximate this. And this is 1.1975. And so the actual sum of the series, which is the sum of k equals 1 to infinity of 1 over k cubed, we know that this is approximately equal to 1.1975. But how good is this approximation? How close is it? Well, we need to find the error when doing the 10th partial sum, and this is called R10. And we know from the previous page that this is going to be less than the integral from 10 to infinity of the function 1 over x cubed dx, and it's going to be greater than the integral from 11 to infinity of 1 over x cubed dx. And so again, I'm just using a lower limit of n for this one and a lower limit of n plus 1 for this one. Well, both of these integrals can be calculated quite easily. We'll go ahead and show that calculation here. All right, so you can pause this video if you like and go through these calculations, but let me just state that this is equal to 0.005, and this is approximately equal to 0.004. So we know that the error when adding the first 10 terms is a number in between 0.005 and 0.004. So we'll focus in on the right-hand side of this. We know for sure the error is no more than 0.005. So this is the maximum value of the error when we add up the first 10 terms. Now let's go to the second question. How many terms are required to ensure that the sum is accurate to within 0.0005? So now we're asking, if we add up the first n terms, so Sn, which is the sum from k equals 1 to n of 1 over k cubed, which is 1 plus 1 over 2 cubed plus 1 over 3 cubed, etc., all the way up to 1 over n cubed, we want to know how many terms do we have to add for that error here to be less than 0.0005. So what does n have to equal? So this is the reverse of the original question. In the original question, we knew how many terms we were adding, and we asked what the error is when we do that. Now we're saying how many terms do we have to add to ensure that the error is no more than 0.0005. Well, again, we know that the error is equal to Rn, and Rn is always less than the integral from n to infinity of the function f of x dx. So in this case, that's going to be the integral from n to infinity of 1 divided by x cubed dx. So now let's just compute the value of this integral. It's going to be the limit as t goes to infinity of the integral from n to t, x to the negative 3 dx. Continuing here, we get the limit as t goes to infinity. We're going to have negative 1 over 2x squared. That is the antiderivative here. You can pause the video and verify that if you want. And then we evaluate this from n to t. And this is the limit as t goes to infinity of negative 1 over 2 times t squared minus negative 1 over 2 times n squared. And this, of course, is equal to 1 divided by 2n squared, because this goes to 0 as t goes to infinity. Okay. So now we know that the error is always going to be no more than 1 divided by 2n squared. But we want our error to be less than 0.0005. So for this to be true, we just need to solve for n here. So this is 1 divided by 2n squared is less than 1 over 2,000. Okay, so 0.0005 is 5 over 10,000, which is 1 over 2,000. I'm going to take the reciprocal of both sides. When I do that, the inequality reverses, and we get n squared is bigger than 1,000 when we divide by 2. Therefore, n has to be bigger than the square root of 1,000. And the square root of 1,000 is approximately 31.6. So we know n has to be bigger than 31.6, which means we need to make sure n is at least 32. So to ensure that the error is less than 0.0005, we need to add up at least 32 terms of the series. If we alter the format of the estimate of the error when adding up the first n terms of a converging series, we get the following formula. The sum of the series is somewhere in between the nth partial sum plus the value of this integral and the nth partial sum plus the value of this integral. This will give us upper and lower bounds on the estimate of the sum of the series. So let's go ahead and take a look at this one. Use n equals 10 to estimate the sum of the series 1 over n cubed, right? So it's the same series we just looked at a minute ago. So what we know here is that the actual sum of the series S is going to be less than or equal to S10 plus the integral from 10 to infinity of 1 over x cubed dx, and it will be greater than or equal to S10 plus the integral from 11 to infinity of 1 over x cubed dx. Now, we just computed the values of these integrals on the previous page, and we also know the value of S10. So we have 1.1975 plus the integral from 11 to infinity was 1 divided by 242, less than or equal to S, less than or equal to 1.1975, plus 1 over 200. Now, if you compute these values on a calculator, you get approximately 1.2016. And on the other side here, we get 1.2025. So if we add up the first 10 terms of the series, that tells us that the estimate of the sum of the series is somewhere in between these two numbers. Okay, so the actual sum of the series is somewhere in between these two numbers. So it gives us an upper bound and a lower bound. We know the sum is at least this value, but no more than this value. And that concludes this video lesson.